Right. So in the last class we looked at what is meant by space lattice, then what is meant by motif, also called basis, motif or basis, then what is meant by a crystal or crystal lattice. Okay, so all these things we discussed in the last class. Then we also discussed symmetry of cubic crystal, right? So symmetry of cubic crystal we discussed. Then we discussed some more basic informations. What we are going to do in this class is that we are going to understand what primitive unit cell, then non-primitive unit cell that is available. Okay, so I am going to introduce you what is meant by primitive unit cell. Take note. Primitive unit cell. Primitive unit cell is also called as simple unit cell. Primitive unit cell is also called as simple unit cell. Okay, I have told you, if you break a crystal into small pieces, okay, you will get smallest pieces, right? You will get many smallest pieces. You take one smallest piece and prepare similar smallest piece in many number, then join them. If you join them, if it is possible to get the crystal, okay, the original crystal again, then that smallest portion is what we call as a unit cell. Okay, so unit cell, primitive unit cell is the smallest portion, is a three-dimensional portion actually. Okay, is the smallest three-dimensional portion of a crystal. Okay, is the smallest three-dimensional portion of a crystal, which when repeated in 3D can produce the entire crystal, or the original crystal, can produce the original crystal. Okay, that smallest portion, okay, is what we call as unit cell. This is actually the definition for unit cell. I'm sorry, this is the definition for unit cell. What is primitive unit cell? This we did discuss in the last class. Now what we are going to do, what is meant by primitive unit cell? Observe carefully. In unit cell we have different types. Okay, primitive, non-primitive, cubic, non-cubic. Okay, now I'll just give you the definition for primitive cell first. What is meant by primitive unit cell? What is the definition? Unit cell is the smallest portion of a crystal. Okay, what is primitive unit cell? Observe carefully. Unit cell in which number of atoms per unit cell equal to 1. Okay, if number of atoms, I am just using atom for understanding purpose, using the word atom. It can be even molecule or particle. Okay, so if number of atoms per unit cell is 1, if number of atom per unit cell is 1, then the unit cell is called a primitive unit cell. Yeah, primitive unit cell. This is the definition. Okay, if number of atom per unit cell is 1, then the unit cell is called a primitive unit cell. Primitive unit cell can also be called a simple unit cell or simple unit cell. So keep this point in mind. Simple unit cell contains, in simple unit cell, number of atom per unit cell is 1. Okay, just for understanding purpose, we also say like this: if only corners are occupied, in the case of cubic unit cell, okay, if only corners are occupied, okay, if only corners are occupied, then the unit cell is called as primitive unit cell or simple unit cell. Simple, let me use the word simple unit cell. This is more appropriate for cubic unit cell. Okay, if unit cell is cubic, then if only corners are occupied, then the unit cell is called a simple unit cell. Okay, keep this in mind. Very simple. Okay, I'll just show you some of the primitive unit cells. In the case of cubic unit cell, if the unit cell is cubic in shape, if only the corners are occupied, okay, I'll just I'm drawing a cube here, and in the cubic unit cell, if only the corners, a cube has 8 corners, if only the corners are occupied, then this unit cell is called a simple unit cell. Okay, remember, unit cell may be cubic, unit cell may be non-cubic, okay, parallelopiped, whatever may be the shape, right? If only corners are occupied, then the unit cell is called simple unit cell or primitive unit cell. In the case of hexagonal unit cell, see, in the case of hexagonal unit cell, this is very important. Yeah, observe carefully. I'm just drawing an hexagon here. Drawing an hexagon. Okay, this is hexagonal shape. Now I'm going to show you a simple hexagonal unit cell, simple unit cell. Okay, what to do? You keep atoms at the corners. These dots may be atoms or maybe molecules or maybe ions. Okay, let me use a general word. Okay, what is the general word? It is something like constituent particles of a crystal. They are all particles. I'm just using a general word, particle. Particle can be atom, can be molecule, can be ions, right? So let me place the atoms at the corners. Then I'll place one atom at the top center and another atom at the bottom center, then 3 atoms at the middle of the hexagon. Listen, in this case, in the case of hexagonal unit cell, this is actually called the simple hexagonal unit cell. Simple hexagonal unit cell. See here atoms not only present at the corners, they also present at the face centers as well as body centers. Okay, or inside the body, right? And this unit cell is called a simple hexagonal unit cell. Keep this in mind, very important. Usually atoms are occupied at the corners, but in some unit cell atoms may present even at the at the other position. A nice example is hexagonal. Okay, and this is called simple hexagonal unit cell. Note down. I have told you already, in those days, people who are doing research in crystals or crystallographers thought that in all crystals only simple unit cell exist. In those days they thought like that. Okay, based on the assumption that only simple unit cell exist, based on the assumption that only simple unit cell exists. Only simple unit cell exists in crystals. Okay. They, based on the assumption that that only simple unit cells exist in crystal, okay, they arrived at 7 crystal systems. They arrived at what is called 7 crystal system. Whatever crystal you take in nature, that crystal should belong to any one of the 7 crystal system. Right? What are they? What are the 7 crystal system? Listen, before going to see the 7 crystal system, let me give you this point called the crystal parameters or unit cell parameters. Okay, let me take a cubic unit cell here, and I'll fix this as the origin. Let's take this axis as x-axis, this as y, and this as z-axis. Observe carefully. Just for understanding purpose, I have taken a cubic unit cell here. A cubic unit cell, or in general, unit cell has 6 parameters. 3 are length parameters and 3 are angle parameters. Listen, along the x-axis, this unit cell makes an intercept here. Let the length of that intercept is a, and y-axis length, let it be b, and z-axis length, let it be c. So 3 length parameters a, b, c. Right? There are length parameters, and there are 3 angle parameters. What are they? Angle opposite to x-axis, that is the angle between y and z, is called alpha. The angle opposite to y, that is the angle between x and z, is called beta, and the angle opposite to z-axis is called gamma. So there are 3 angle parameters, alpha, beta, and gamma. Altogether, there are 6 parameters. There are 6 parameters. So, by varying these 6 parameters, a, b, b, c equal, a, b, c not equal, by varying this, right, we can mathematically create 6 factorial arrangements. So it will comes out as 720 different shapes. So in those days, listen, a unit cell has only 6 parameters. By varying the 6 parameters, right, theoretically we can form 720 different types of crystals. But out of these, only 7 are actually existing in nature. This is the thing which was found by the researchers. So out of 720, only 7 exist. Only 7 exist in nature. Only 7 exist in nature. Right? And those crystals are called as 7, that 7 different types is called as 7 crystal system. Okay? So here, usually in cubic unit cell, if only corners are occupied, it is called simple unit cell. But this is an exception. Hexagonal unit cell. This hexagonal unit cell consists of corners. Corners are occupied, and apart from corners, see, the top center and the base center are occupied, and 3 particles are present at the middle of the hexagon. And this unit cell is called a simple hexagonal unit cell. This itself is called a simple. Okay, this is actually an exception from cubic. Right? Note down. It's very important. So 7 crystal systems. 7 crystal systems. Remember, this 7 crystal system is developed based on the assumption that only simple unit cell exists. So, what is the assumption? The assumption here is that, right, only simple unit cell exists. Simple unit cell exists. Only simple unit cell exists. Based on this assumption, right, people have found out 7 crystals in nature. Actually, 720 possibility are there. Okay, 720 possibility are there, but out of 720, only 7 exist in the nature. Crystallographers found only 7, right? And remember, in these 7, the assumption is very important. They have assumed that only simple unit cell exists. Now, what are the 7 different types of crystal system? Let me write here. 1, 2, 3, 4, 5, 6, 7. Okay. I'll just suggest you, just remember in this order. In different book, the order is given in a different manner, but I'll suggest all of you, please remember in this order. The order is this: C, T, O, M, T, R, H. Just remember in this order: C, T, O, M, T, R, H. C, T, O, M, T, R, H. What is C here? C is nothing but cubic. T means tetragonal crystal system. O means orthorhombic. M means monoclinic. T means triclinic. H means rhombohedral crystal system, and H means hexagonal crystal system. Okay, so in 7 crystal system, yes, we have these 7 different types: cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, and hexagonal. Now I'll give you the details about the parameters. Okay, first we'll see the length parameters, then we'll see the angle parameters. First I'll give you the length parameters. What are the different length possible for these systems? Okay, let me write here. Let me write the length parameters first. Okay, what are the length parameters? For cubic, the length parameters are such that A, B, C, X intercept, Y intercept, and Z intercept all are equal. Then angles alpha equal to beta equal to gamma, all the angles are equal, and it is equal to 90 degree, exactly 90 degree. Okay, so you take any unit cell, if the intercepts are equal and if all the alpha gamma angles, right, alpha beta gamma are equal to 90 degree, then that unit cell is called a cubic unit cell. Then what is meant by tetragonal? In tetragonal, listen, A equal to B but not equal to C. 2 sides are equal, one side is not equal, and alpha equal to beta equal to gamma equal to 90 degree. No change in this. Okay, it is something similar to cubic. Then what is orthorhombic? In orthorhombic, A not equal to B not equal to C. All the 3 lengths are not equal, but the angles are equal. Alpha, beta, gamma are equal, and it is equal to 90 degree. This is orthorhombic. Okay. See the way that I am writing here. It's very simple. First, all are equal. Second, one length is not equal. Third, 2 lengths are not equal. Keeping these things as such. That is why I have told you, remember in this order. Okay. Then monoclinic. What is monoclinic? Listen, clinic means non-90. That's a meaning for clinic. Clinic means non-90. Monoclinic means one of the angle is non-90. Okay. So in monoclinic, see, A, just keep this as such. A not equal to B not equal to C. And out of the 3, one is non-90. What is that? Alpha and gamma are equal to 90 degree. Beta is not equal to 90 degree. One of the angle is non-90. One of the angle non-90. So it is called monoclinic. Clinic means non-90. Okay. Then what is triclinic? Tri means 3. Triclinic means all the 3 angles are non-90. So A not equal to B not equal to C. See, all the 3 lengths are not equal. And alpha not equal to beta not equal to gamma, and they are also not equal to 90 degree. Okay, all the three angles, they are not equal. They are also not equal to 90 degree. Okay, that's why it is called triclinic. They are not equal to 90 degree. So this is actually called the least symmetric crystal, because sides are not equal, angles are not equal. So this is the least symmetric crystal, right, which is available in 7 crystal system. Least symmetric. Then I'll come to rhombohedral. For rhombohedral, all the 3 sides are equal, A equal to B equal to C. All the angles are also equal, alpha, beta, gamma, all are equal. Something similar to cubic, see, A equal to B equal to C, alpha, beta, gamma equal to, they are all equal, but the only difference is it is not equal to 90 degree. In cubic it is equal to 90, whereas in rhombohedral they are not equal to 90 degree. Then last one, hexagonal. In hexagonal, A equal to B but not equal to C. Alpha and beta are equal to 90 degree, but gamma is equal to 120 degree. Right? Take down. So this is the way by which crystallographers found that the 7 crystal system exists in nature. Right? And in those 7 crystal system, and these are all the parameters exist. Okay? Take down. So non-primitive unit cells, primitive unit cells also exist in crystallographers. They found out that yes, in crystals non-primitive unit cells also exist. Right? What are the non-primitive unit cells possible? One is called body-centered unit cell, body-centered unit cell. Then face-centered unit cell, face-centered unit cell, and third one, end-centered unit cell. End-centered or edge-centered? End-centered. I'm sorry, end-centered. End, C-N-T-E-R-E-D, centered unit cell. Okay? Body-centered, face-centered, end-centered. What is body-centered unit cell? I'll take cube as an example. I'll take a cube. Listen. Apart from atoms at the corners, we have an atom present at the center of the cube. If an atom present at the center of the cube, apart from corners, then that unit cell is called body-centered unit cell. If I take a cubic, then it is called body-centered cubic unit cell, BCC. Body-centered is general term. If you take a cubic, then it is called body-centered cubic unit cell. Body-centered cubic unit cell. Then what is meant by face-centered? Let me take cube as an example, because it is somewhat easy to draw cube, that's why. Now I'll place the atoms at the corners. Apart from corners, atoms or particles also present at the face centers. You know very well, a cube has 6 faces. So I'll place one atom at this face center, one atom at the top face center, one atom at the face center of this face, one atom at the body base center, one at the front and one at the back. Okay, see, I have placed 6 more atoms in the face centers, and this is what we call as face centered unit cell. If you take a cube, then it is called face centered cubic unit cell, FCC. Okay, the general term is face centered. If you take a cube, then it is called face centered cubic unit cell. Right, what is meant by end centered? End centered unit cell is a special type where I'll take a cube like unit cell. Apart from corners, all the corners are occupied. apart from corners, we have two atoms at the opposite phase centers. Suppose I'll place one atom in this phase, the another atom is present in the opposite phase. If we have two atoms present at the opposite phase centers, other phase centers are empty. You take any two opposite phases and place one atom in each phase at the center. Then it is called end-centered unit cell. If you take a cube, then it is called end-centered cubic unit cell, ECC. Okay, take note. So we have simple unit cell. So what are the different types of unit cell we have? Unit cells, right? Simple unit cell, let me write simply SU, simple unit cell, body centered unit cell, face centered unit cell, and end centered unit cell. Body simple unit cell, body centered, face centered, end centered unit cells. Okay, so we have 4 different types of unit cells, right, in crystals. Now again people have started to identify how many crystals are actually exist, because now apart from simple simple unit cell, we also have body centered, face centered and all, right? So again crystallographers started to analyze, right, the primitive and non-primitive unit cells, right, that exist in the crystals, right? And a scientist, Bravais, he finally came out that he found 14 different types of crystals exist in nature. Okay, based on the existence of, or based on the presence of simple as well as non-primitive unit cells. Okay, primitive and non-primitive unit cells. Based on these, right, he analyzed different crystals and he found that there are 14 different types of crystals exist. Right? What are the 14 different types? Yes, we are going to discuss now. Right? Bravais, lattices or lattice. Bravais lattices. Okay, Bravais found out that, okay, whatever crystal you take, that crystal must belong to any one of these 14 different types. Any one of the 14 different types of crystals, right? It is called Bravais. These crystals are called Bravais lattices, right? What are the 14 different types? 1, 2, 3, 4, 5, 6, 7. First, I'll write this 7 crystal system. Okay, CTOMTRH. Remember in this order. C means cubic, T means tetragonal, O means orthorhombic, M means monoclinic, and this T is triclinic, right? R means rhombohedral, and H means hexagonal. Okay, there are 7 different types. Listen, these 7 types are based on the assumption that only simple unit cell exists. Okay, but now people have found out non-primitive unit cell. So in each case, how many different types of crystals exist, unit cell exist, right? In all the types, yes, we have simple. No doubt in that. In all the 7 types, simple is there. Cubic, yes, simple cubic unit cell is available. Tetragonal, simple tetragonal is available. Orthorhombic, simple orthorhombic is available. Simple monoclinic is available. Simple triclinic is available. I'll just put, see, this is ST, this is also ST, but try to understand the meaning. Okay, I'm just using a different symbol here. T, small t, capital T, small t. Okay, this is simple tetragonal, this is simple triclinic. Then simple hexagonal unit cell. Simple hexagonal, I'll put SH. Then we have, simple rhombohedral, then simple hexagonal. Okay, in all the 7 types, simple unit cell already exists, we know. What we don't know is that in each of these 7 types, how many non-primitive unit cells exist? Right? And what are they? What are they? Number 1. See, in the case of simple cubic, we have body-centered unit cell called BCC, body-centered cubic. Then we also have face-centered cubic. So in cubic, we have these 3 types of unit cell exist. Whatever cubic crystal you take in nature, whatever crystal, it must belong either to simple cubic or BCC or FCC. End-centered is not possible in cubic. Then tetragonal. In tetragonal, we have simple tetragonal and body-centered tetragonal, BCT. In orthorhombic, yes, this is the special type where all different types exist. Simple orthorhombic, body-centered orthorhombic, face-centered orthorhombic, and end-centered orthorhombic. All the 4 types exist in orthorhombic. In monoclinic only 2, simple monoclinic and end-centered monoclinic, only 2 exist. Simple and end-centered. In triclinic, only simple. In rhombohedral, only simple. In hexagonal also, only simple. So here, observe carefully. Here we have 3 types. Here we have 2. Here we have 4. Here we have 2. Here we have 1, 1, 1. If we add them, 3 plus 2, 5, 9, 11, 11 plus 3, 14. Yes, there are 14 different types of crystals exist in nature. Okay, take down. And these crystals are called as Bravais lattices. We have 14 Bravais lattices. Right? Take down. Okay. So in
corner lemot atoms.
Wait. Out of 7 crystal system, out of the 7 different types, and in each type we have subclasses also. Out of 7, I am going to discuss, or I am going to focus only on focus on cubic crystal and hexagonal crystal. Okay, remaining crystals, usually for a competitive examination, they won't ask questions much beyond the length and angle parameters. Okay, so we are going to focus only on simple cubic bodies, cubic crystals and hexagonal crystals here. Observe carefully. In cubic crystal, we have 3 different types: simple cubic, body-centered cubic, and face-centered cubic. Right? Some crystals, some cubic crystals have simple cubic unit cell. Right? I have drawn a cube here, and I'll place atoms only at the corners. If I place atoms only at the corners, then it is called simple cubic. Right? This is called simple cubic unit cell. Now what I am going to do, I am going to find out number of atom per unit cell, also called rank. Number of atoms per unit cell. Number of atoms per unit cell. Okay. Remember, each corner atom of a cube is shared by 8 unit cells. Each corner atom is shared by 8 unit cells. Right? Therefore, to find the number of atoms per unit cell, first you find out how many corner atoms are there. And remember, each corner atom is shared by 8 unit cells. Therefore, the contribution of each atom to one unit cell is 1 by 8. So, there are 8 corner atoms, 8 into 1 by 8 equal to 1. So, number of atom per unit cell for simple cubic is 1. Okay, number of atom per unit cell is also called as rank. Sometimes it is called as rank of the unit cell, rank. So, rank for simple cubic unit cell is 1. Okay, note down. The next unit cell that we are going to focus is BCC. In BCC, all the corners are occupied and one atom present at the middle of the box. It is called body center. Okay. These corner atoms are shared by other unit cells, whereas the body center atom is not shared by other unit cell. It belongs to only this unit cell. Okay. So for corner atom, number of corner atom into 1 by 8 we should multiply. For body center, you need not multiply with any value here because each body center atom is shared, and it is for that unicell only. It is not shared by other unicell. So here we have 8 corners, 8 into 1 by 8, and we have one body center, so plus 1. This is 1 plus 1 you will get, and the answer is 2. So rank of body center cubic unicell is 2. Take note. In face center cubic unicell, so let me draw a cube first. Cube. Then all the corners are occupied by atoms or particles. Apart from the corners, atoms also present at the centers of each face. So in cubic unicell there are 6 faces, 2, 3, bottom 4, front 5, back 6. Okay. Observe carefully. What is the rank? What is the rank? Number of corner atom into 1 by 8 plus face center atoms are shared by 2 unit cells. So contribution to 1 unit cell is half. So number of face center atom into 1 by 2. Face center atoms are shared by 2 unit cell. So contribution to 1 unit cell is 1 by 8. Therefore, number of corner atom 8 into 1 by 8. Number of face center, totally 6 face center atoms are there. So 6 into 1 by 2. This is 3, this is 1. So you will get the answer as 4. Rank of face centered cubic unicell is 4. Take note. So here number 2, diamond cubic crystal. Diamond cubic crystal. What is diamond cubic? Is actually cubic, right? But it has some special atoms are present at the different places. Okay. So diamond cubic is very special, right? What is diamond cubic? Listen, you take a cube. I am drawing a cube now, and I'll show you how diamond cubic crystal, right? How the atoms are present at the diamond cubic crystal. In diamond cubic crystal, you place atoms at the corners. All the corners are occupied. Now, listen, I am going to draw diagonals. Observe carefully. Let me draw one diagonal here, this corner to this corner. Observe carefully from this corner to this front corner. Okay, I am drawing a diagonal. The length of the diagonal, let it be 1 unit, and take 1 by 4. This is 1 by 4 position, and place an atom here. Okay, you draw a diagonal from one corner and place an atom 1 by 4 distance from that corner. Then take this center or this corner and join to the opposite corner. Observe carefully. I am going to use different color. I'll take this corner. I am connecting to the opposite corner like this. Observe carefully. I am just joining this corner to that corner. Now from this corner at 3 by 4th position, I am going to place an atom. From here, 3 by 4th position is close to this atom. This is another atom. Then I'll take this point and connect this point to the opposite corner. Okay, diagonally opposite corner. Diagonally opposite corner. Now I'll place an atom at 1 by 4 position from this corner. Okay, at 1 by 4 position. So let me approximately here along this corner. Okay, at 1 by 4 distance from this corner, at 1 by 4 distance an atom is present. Then from this corner I'll connect this corner to that corner, and from here, from this point, take 3 by 4th distance and place an atom here. 3 by 4th distance, place an atom here. So very simple. Take all the 4 corners and connect it to the opposite corners. Okay, diagonally opposite corner. Place the first atom at the 1 by 4 distance, second atom 3 by 4 distance, third atom 1 by 4, fourth atom 3 by 4. That's all. Listen carefully. This is diamond cubic. In diamond cubic, rank, number of atoms per unit cell. What is the rank? Rank for diamond cubic is this. Listen. We have 8 corner atoms. So number of corner atoms. Each corner atom is shared by 8 unit cells. So I'll put the formula NC into 1 by 8 plus number of body center atoms. Listen, they are not center actually. I am just writing this as body center atom, but it is not center, it is inside the body. Okay, so we have 8 corners, 8 into 1 by 8 plus we have 4 atoms present inside, which is not shared by the other unit cell. Listen carefully, we have 4 atoms inside. Those 4 atoms are not shared by other unit cell, which means all the 4 atoms belong to this unit cell only. So you just add 4 as such. Okay. Take down. Then, and I have showed corner atoms here. Now few more atoms are there where they are all present at the face centers. One at this face center, another at this face center, another here, another front, bottom face center, front face, back face. So corners, face centers and diagonal positions. Okay, so we have face center also. Number of face center atoms and each face center is shared by 2. So NF into 1 by 8, 1 by 2 I'm sorry. And how many faces? For a cube there are 6 faces. So 6 into 1 by 2, right? So what we get is 1 plus 4 plus 3, we get 8. Rank of diamond cubic is 8. Take down. This is not simple. This is actually a non-primitive unit cell, right? But it is a special case. It's a special case, right? So we discuss this separately under the heading diamond cubic. Okay, take down. Okay, now let me move on to the hexagonal unit cell. Hexagonal unit cell, and in hexagonal unit cell, I have told you we have only one type. That is simple. Okay, so we are going to focus on simple hexagonal unit cell.
Sir, on the page அப்படியே ஒரே நிமிஷம் சார் போட்டோ
பண்ணிட்டீங்களா? After a diamond cubic, now we will discuss hexagonal crystals. Hexagonal crystals. I have told you in hexagonal crystal only simple hexagonal unit cell exist. Okay, simple hexagonal unit cell. Only simple hexagonal unit cell exist. Right? How does it look like? See, let me draw here. Yes, this is the simple hexagonal unit cell. Okay, the simple hexagonal unit cell. In simple hexagonal unit cell, all the corners are occupied by atoms or particles. All the corners 1, 2, 3, 4, 5, 6. All the corners are occupied, and all the bottom corners are also occupied. All corners are occupied, and top face center, bottom face center also occupied. Then there are 3 atoms present at the body centers. Okay, now this is simple hexagonal unit cell. What's the rank for this? What is the rank of this unit cell? Let me write here. Rank. What is rank? Rank is nothing but number of atom per unit cell. So we have corner atoms Okay, number of corner atom. In hexagon, each corner is shared by 6 unit cells. So each atom contribute only 1/6 to 1 unit cell. Plus number of body center atoms present inside the unit cell, it is not shared by other unit cell. So whatever number of atom present inside the body, you just take them as such. Plus phase center atoms are shared by 2. Number of phase center shared by 2, so 1/2. So here we have 12 corners above. See, in top we have 6 and bottom we have 6 corners. So 12 plus 6 plus 6, 12. 12 corner atom. Each corner atom is shared by 6 unit cell. And there are 3 body center and face center, top face, bottom face we have 2 into 1/2. So this gives me 2 plus 3 plus 1, nothing but 6. Take down. Rank of simple hexagonal unit cell is 6. Take down. The next point is about packing fraction of different crystals. How to find packing fraction. How to find that. Okay, let me take a simple cubic unit cell first. Simple cubic. We'll find out packing fraction for simple cubic unit cell or simple cubic crystals. Listen, in simple cubic, let me draw the cube first. Cubic unit cell, so let me take a cube. Right, and we'll place the atoms at the corners. 1, 2, 3, 4, 5, 6, 7, 8. Observe this carefully. In cubic, all the side lengths are equal. So this side length, let it be A. Similarly, all the side lengths are equal. Now, listen, just for understanding purpose, for our convenience, we have drawn the unit cell in larger size and we place the atoms at the long distances, right? But in reality, the corner atoms are actually touching each other. In simple cubic, see, let me show you. This is the top view. From the top, if you see how the atoms look like, see, from the top, if you see the atoms, they are actually touching each other. This is from the top view. Actually, while drawing, we comfortably or we conveniently placed atoms at the corners and we'll draw large size unit cells and all. But in reality, the top atoms, right, 4 atoms, they are actually touching each other. If you join their centers, take the centers of each atom, if you join them, you will get a square shape. If you view from the top, you can see the square shape. Okay, now listen, this length from this center to this center, this length is actually A. Edge length, it is also called edge length. Edge length. Now, all the atoms are similar atoms here. Therefore, if this is the radius of one atom, this is the radius of the other atom. Since all the atoms are same, this radius and that radius are one and they are equal. So in this case, A, edge length A is supposed to be equal to 2 times R. Okay, take note. Packing fraction. Packing fraction, let me write simply PF. Packing fraction is nothing but volume occupied by the atoms in the unit cell. Volume occupied by the atoms. I am just using the word atoms here, but in crystal, okay, instead of atom, molecule may be there, ions may be there, okay. So whatever it is, volume occupied by the particles divided by volume of the unit cell. Volume of the unit cell. This is the packing fraction formula. Now, listen carefully. We know very well, in the case of simple cubic, rank is nothing but 1. So, what is the volume occupied? Volume occupied is nothing but rank of the unit cell into each atom. Atoms, we are assuming atoms as spherical in shape. Therefore, for each atom, the volume is 4/3 pi r cube. where r is the radius of the atom or radius of the particle. What is the volume of the unit cell? The unit cell is cubic in shape. Okay, it is perfect cube. Therefore, volume should be A into A into A. This is the volume, right? What is the rank for simple cubic? For simple cubic, rank is 1. So 1 into 4 by 3 pi r cube by what is A? A is equal to 2r. So A cube is equal to 8 into r cube. R cube cancel each other. So this is actually 8 by 1. If I bring it to the multiplication, we get 4 by 3 into 22 by 7 into 1 by 8. Okay, if you simplify this, right, you will get a value which is roughly 0.52 something. Let me give the exact value here. One second.
5.4, sir.
So the value comes out as 0.5238 exact. Right? Actually, it is going after 8. We have 0, 9, 5, 2 something. But after the decimal point, if you take 4 digits, that is sufficient. So this is the packing fraction for simple cubic. Okay. Or in percentage, we can say it is 52.38%. 52.38%. So what does it mean? It means that if you take the volume of the unit cell as 100%, if you assume the volume of the unit cell is 100%, then out of 100%, only 52.38 is occupied. That's the meaning of packing fraction. Remaining space, that is nearly 47 point something, the nearly 47 point something percentage, it is actually empty space available in the unit cell. So this is packing fraction. What is the percentage of empty space? Percentage empty space. Percentage of empty space in the unit cell, it is nothing but 100 minus this value, 52.38. Right? It comes out around 47 something. Let me give the exact value. 52.38. Yeah, I am getting 47.62%. Observe carefully. 47.62% of the unit cell is empty. Only 52% is occupied in the simple cubic. Okay, so in simple cubic there are more empty spaces are available. So the crystal is not stable. The crystal is not stable. You know very well, in the periodic table, in the entire periodic table, only one element, polonium, exists in simple cubic form. Because simple cubic unit cell or simple cubic crystal is not so stable because it has more empty space. Right? So you cannot make a stable crystal with this empty spaces. Okay, it's not possible. Right? Take two. So that's the reason why many elements, they form different unit cell, right, except simple cubic. Simple cubic is not that stable. The next one is the body center cubic unit cell. So here I have drawn the body center unit cell, body center cubic unit cell. Okay. Now observe carefully. In body center, see, this is edge length. If you view from the top, the carbon atoms are not touching each other. Observe carefully. We have 4 atoms. We have 4 atoms. I am just view this crystal or the unit cell from the top. It's a top view. From the top view, we have 4 atoms here. These 4 atoms appear like this. They are not touching each other. And if you join the centers, of these atoms, you will get a square shape. Perfect square shape. And we have an atom inside. See, if you view from the top, we have an atom inside. That atom is present just below these 4. Correct? We have 4 here. Just below these 4, this atom is present. So let me show it in dotted lines. dotted lines. That atom, which is actually below these four, that atom touching these four atoms. Okay, the middle atom touching these four corner atoms. Also, this atom touches the bottom four corner atoms. So the body center atom touching the surface of all the corner atoms. That's the point. Okay, now how to calculate the packing fraction for body center cubic unit cell. Okay, so what we have to do? Listen, I'll take this corner as A, right, and this corner as B, and this corner as C. A, B, C. Now what I'm going to do, first I'll take this diagonal. Observe carefully, I'm taking the diagonal AC, right? Actually the center atom touching the surface of A as well as touching the surface of C. I have told you, the center atom touches the surface of all the above four corner atoms and below four corner atoms. So A, center atom touching A as well as C. So it is somewhat look like this. See, A atom, this is the center atom, and this is the C atom. So this is the point, this is A, this point corresponds to A, and this point corresponds to C. A, C. Right, now if we connect these, this is the diagonal, body diagonal, which is equal to, see, this is radius of one atom, here we have diameter, so R plus R, here we have R. Therefore body diagonal AC is equal to 4 times the radius, okay. We can also find this body diagonal AC using this triangle. See, I'll connect A and B and C, and here we have right angle. So ABC is a right angle triangle. See, in triangle ABC is a right angle triangle. AC is the hypotenuse. AB and BC, they are adjacent sides. Okay. So according to Pythagoras theorem, AC square equal to AB square plus BC square. Okay. What is AC? AC is equal to 4R. So 4R square, let me write like this, 4R square equal to AB. What is AB? This AB, listen, this length is A, this side length also A. So I'll take this triangle, that is AB, C, I'll take this as D. I'll take the triangle ADB. In triangle ADB, observe carefully, AB square equal to AD square plus DB square. AD is A, small a square, and DB also A, small a square. So you'll get 2 times A square. This is AB square. So I'll put this value here. So AB square equal to 2 times A square plus, what is BC? All side lengths are equal, like this is cube. So all side lengths are equal. So BC is equal to A, so A square. So this is, this we can write it as 4R the whole square, right? So 4R the whole square equal to 3 into A square. If we take square root, we get 4R equal to root 3 into A, or R is equal to A into root 3, I'll write A in front, A into root 3 by 4. This is the relation between radius and A for body centered cubic unit cell. Or you can also write like this, A is equal to 4 by root 3 into R. You can also write like this. Okay, take down. This is the relation between edge length and radius of the atom for BCC unit cell. Take down this. Now I'll show you how to calculate packing fraction. This is packing fraction for BCC. Packing fraction can also be called as packing efficiency, right? So what is packing fraction for BCC? Simple, rank of the unit cell into volume occupied by each atom, 4 by 3 pi r cube, divided by volume of the unit cell. Since the unit cell is cube, so volume of the cube is A cube. What is the rank for body center cubic unit cell?
2.
2, yes. 2 into 4 by 3, pi value 22 by 7 r cube, divided by A is equal to 4, just now we wrote, A is equal to 4 by root 3 into r, 4 by root 3 into r, 4 by root 3 into r whole cube, because A cube is there. So this is equal to 2 into 4 by 3 into 22 by 7 into, here you see r power 3, this is r cube, here r cube cancel. We get 4 by root 3 r whole cube, okay, 4 by root 3 whole cube. If we bring it to multiplication, we will get root 3 by 4 into root 3 by 4 into root 3 by 4. Because we have cube here, I just bring it to the multiplication, so we will get this. Right? This 4 and this 4 you can cancel. 1 2s are 2, 2 2s are 4, 1 2 11 we can cancel. So remaining things you have to multiply. Root 3 into root 3 is 3, so this also you can simplify. 11 into 3 into root 3 by here we have one more 3, so 3 into 7 into 4, this 3 you can cancel. So it is very simple, 11 into root 3 by 7 into 4. This is what we need to find out. And root 3 is 1.732, so I'll just give you the value. 11 into 1.732 is equal to divided by 7 equal to divided by 4. Yeah, it comes out as 0.6804. 0.6804 as the packing fraction. Right? What is the percentage packing fraction? Percentage is, just multiply this by 100, 68.04 percentage. 68.04 percentage of the unit cell is occupied. Remaining 100 minus 68.04, it is roughly 31.96 percentage, roughly. 31.96 is empty space, percentage empty space in the BCC. Empty space is somewhat less. If empty space is less, then stability will increase. Okay, take note.